So the paper that we're going to present to you today, I hope you can see my screen. It should be visible now.
Yes.
Clean hydrogen. Yes, thank you. It's called Clean Hydrogen Deployment in the Europe-MENA region. As Mario also mentioned, the paper, just for all the participants, the paper will be published by the end of the month, and we'll make sure that you will get a copy. It's a Fraunhofer CINES paper, but we've worked in close collaboration on this paper with Geostock for several parts of this paper. So first, a few words about the Fraunhofer CINES hydrogen network. So CINES stands for the Cluster of Excellence Integrated Energy Systems and consists of 5 core institutes and 7 partner institutes. So we conduct research all along the hydrogen value chain, but CINES is also an exchange and cooperation platform. So not all of the institutes that are in CINES are going to present today, but the ones that are, we have also listed the cities in which they are located. So Mario Rakwitz is located in Cottbus and Marieke Welisch in Berlin, and my other 2 colleagues are in Kassel, and I myself am in Freiburg. So, like I said, we have expertise all along the hydrogen value chain, from materials to the energy sector to systems, technology production. And we look at hydrogen production, storage, hydrogen conversion, transport infrastructure, and hydrogen end users from the steel industry to the power sector and the mobility sector. So my name is Jan-Frederik Braun. I'm a senior expert hydrogen economy for the MENA region. So my main work for Fraunhofer CINES is the development of research and the development of research projects in the MENA region. Felix?
Good afternoon. Hello. So I'm Felix Frischmuth here in Kassel, and I'm a research associate at Fraunhofer IEE since 2019. I work in the group Energy, Economics and System Analyze, and my main focus here is on techno-economic optimization models for the energy transition of Europe.
Good afternoon. My name is Richard Schmitz. I'm also working at the Fraunhofer IEE in Kassel. I'm also a member of the Energy, Economics and System Analysis group. And I mostly work with our energy system model scope scenario development, which will be introduced later.
Thank you, Richard. Now, just before I'm going to continue, I just want to quote the great Anthony Hopkins in the fantastic first season of Westworld, where he plays a brilliant scientist who engages in all kinds of mischief with robots. But he says something very interesting, and he says that evolution forced the entirety of life on this planet using only one tool, mistake, and that humans are the product of a trillion mistakes, and that you must indulge me in the occasional mistake. This is fitting for our paper because we are also indulging in a lot of mistakes. I think that our research is a work of trial and error. As all good research, you can learn a lot from making mistakes. So what we're going to present here today is certainly not the alpha and the omega, but it is certainly holds a lot of interesting points and content for further development and further elaboration. So what we've done in our study is we have taken the target of Repower EU of 20 million tons of hydrogen production and import. We've taken that as a benchmark because that is a political target that's been set by the European Commission and by the European Union at large. So the European Union is planning to produce those 20 million tons by 2030. And we have taken that as a benchmark to ask the following questions: which hydrogen production and import volumes in the Europe-MENA region are technically feasible? Can imports from the MENA countries be integrated into the existing European natural gas infrastructure? And also, what amount of technical storage capacity for hydrogen is available in the Europe-MENA region? And which socio-economic issues must be included in a strategic analysis of the clean hydrogen value chain in the Europe-MENA region? It's important for our research and for the focus, also for the setup and the content of the paper that we are discussing today, is that we're looking at various potentials. So a large extent of our analysis is focused on the technical economic potential of developing a hydrogen economy, because we sometimes hear a lot of numbers, a lot of announcements, but it's not really always clear what that really, like, basically what kind of different dimensions have been taken into account. And we here in our paper, we try to also create some solid conceptual clarity by what we mean by various potentials. So we look at technical economical potentials, but we also look at, for example, the socio-economic potential of hydrogen production. And the socio-economic potential also has a very strong ecological aspect to it. So there's a bit of overlap there. A couple of definitions. First of all, the MENA region. The MENA region consists, according to the World Bank, of 21 countries. What we've taken for the purpose of this paper is we have taken 6 of those MENA countries. That is Morocco, that is Algeria, Tunisia, Libya, where I am right now, Egypt, and Saudi Arabia. We have chosen those countries due to their geographical proximity, their already existing infrastructure, and their capacity for low carbon hydrogen production. We've defined Europe as consisting of the member states of the European Union, plus Great Britain, Switzerland, and Norway. And different from Repower EU, we focus on clean hydrogen. Repower EU focuses almost exclusively on green hydrogen, so that is renewable-based hydrogen, but we take a broader focus. So we more look at the carbon footprint of hydrogen, because we want to take it into consideration that is also of great interest to the MENA countries, because they have a lot of already existing gas infrastructure, for example. So that's a bit on the conceptual clarity of the paper, and I now want to give the floor to my colleague Richard Smits to talk a little bit about the methodology.
All right, thank you for the introduction. With this, I would like to start the methodology section, in which I would like to introduce our models and also the data that is behind our analysis and the ongoing paper. What you can see here is the model linking approach that is used by us. It consists of 2 different models, namely the energy system model scope scenario development, or short scope SD, and the gas market model Imagine, which is a short form of infrastructure and market transformation for gas in Europe. So we start with the energy system model scope SD, which covers the heat, power, and transport sector to model long-term decarbonization scenarios, but it does not contain gas infrastructure. And this is why we also use the Imagine model, which then minimizes all investment and operation costs for both hydrogen and methane infrastructure and markets in a daily resolution, and also for several planning periods. So the data that is given from Scope SD to Imagine is, besides others, fuel demands and electrolyzer productions. And by the linking of these 2 models, we can allow for a cost-optimal analysis of clean hydrogen production, demand, transport, and also storage developments by a given hydrogen demand in Europe. Felix, you're muted.
Sorry, I have to mute. Yeah. So another tool used in our study here is the Fraunhofer Global PTX Atlas, which is a WebGIS application that identifies worldwide potential production site of electricity-based fuels, including hydrogen in gaseous or liquid form, and other derivatives like ammonia, methanol, or Fischer-Tropsch by 2050. While the primary goal of the PTX Atlas is the analyze which regions can produce significant amount of PTX fuels and at what cost. A particular focus is on defining the techno-economic potential under strict sustainable criteria, or here called exclusion criteria. Standard parameters like the level costs of electricity for PV and wind, but also other parameters like nature conservation, limited water availability, infrastructure, for example, the distance to ports or pipelines or cities, and other unsuitable areas were considered in this tool. So this exclusion parameter leads to considered and excluded areas On the bottom here on the slide, you can see this for the African MENA region, so the North African MENA region part. But the global PTX atlas also allows for a socio-economic analysis. Note that this is a high-level country analyzes socio-economic potential of the PTX exporting countries by calculating the individual values of 40 indicators and 70 associated indices in 6 schematic areas. You can see on the lower left corner. So, for example, there are the economics, politics, society, technological, and natural conditions. All indices are based on studies, calculations, and statistics from public, national, and international organization or private consulting groups. Intervals are formed from the individual values of the indices, each of which was assigned a value between 1, which is highly negative, and 5, which is highly positive. So with this set of tools we presented here, I will hand over to my colleague Richard.
All right, thank you. This is the beginning of the results section for Europe. The results section for the MENA region will follow up later. You can also switch to the next slide. What is generally important to mention before I start talking about it is that our analysis is based on several prominent scenarios, including the ENSO-E and ENSO-G scenarios, and also on the implementation of the European Union's climate targets. So what we can see in this chart is the European hydrogen demand in terawatt hours, which can be covered by import and also by domestic production, so hydrogen production in Europe. So our cost optimization analysis shows that Europe's hydrogen production capacity could reach around 143 terawatt hours, which is the same as 4.3 million tons by 2030, and that later Europe will possibly reach the Repower EU production target of 10 million tons that was already introduced by Mario Rackwitz sometime between 2035 and 2040. If you go to the next slide, perfect. This is once again the European hydrogen demand, but this time it's divided by sectors. The data sources that we've used here are once again ENSO-G, ENSO-E, but also the German Network Development Plan, the Netzentwicklungsplan, and some industrial hydrogen demand estimations by Agora Energiewende. So what we can see is that the industry is by far the largest consumer in all years of hydrogen, and that over time the consumption of refinery decreases, whereas consumption of transport and power plants increase over time. So Europe will require approximately 2,000 terawatt hours of clean hydrogen by 2050, whereas in 2030 a demand of around 376 terawatt hours can be seen. And this contrasts with the Repower EU target of producing, importing, and transporting those 20 million tons of hydrogen by that same year. So what we have seen on the last slide was an overview, an European overview until 2050 in 5-year steps. And what we can see here is the hydrogen consumption and also production per country, and only for the year 2030. So in the bars, you can see the hydrogen consumption per sector. And what strikes out first is that Germany has by far the highest consumption in Europe, followed by the Netherlands and Great Britain. And on the purple line, this indicates the domestic production potential for each country. And we can see that there is no direct correlation between consumption and domestic production. So for example, if we look at Germany, we'll see that Germany relies on imports, and that it will probably face a gap between production and sectoral consumption of approximately 1.8 million tons or 60 terawatt hours in 2030. Whereas, for example, the Netherlands or Spain can almost produce as much as they will consume. If we go on one slide, this is pretty much the same setup. Now it's the year 2050. We can see that Germany is still the top consumer, followed by France on the second place now. And we also see that there are other countries poised to become significant importers by 2050. For example, Belgium, Poland, the Netherlands, and also Italy, which means that Northwestern Europe is a significant hydrogen importer, led by Germany, so to speak. If we have a small look at the different sectors, you can see on the legend on the right side, we can see that from 2030 to now 2050, the refineries are almost gone, and we can see more demand in the transport sector. And also, we see a higher usage of hydrogen for power plants.
Okay, so I will go on with the next 3 slides, which will show the results of our optimization model Imagine, which is based on the scenarios you've seen in the last slides. As you can see, our technical assessments show a decrease in natural gas storage capacity as expected in red bars, especially in the long term and expansion of hydrogen storage, which we assume are salt caverns up to 2050 is grown up in the green bars. This was amount to around 216 terawatt hours of installed capacity by 2050, which is a massive increase. Most of this would consist of new capacity in the dark, you can see in the dark green bars, and would need to be carried out in the 5 countries, Germany, France, Great Britain, Poland, and the Netherlands. This is due to the fact that most of the salt caverns, which are suitable for long-term seasonal hydrogen storage, are located in this region, as well as they are the greatest importers. So in our case, technical installed capacity means the maximum storage potential that could be utilized without considering some other aspects we saw in the beginning of the presentation, like ecological or social considerations. In our analysis, the need for hydrogen storage before 2045, you can see, is relatively low compared to today's natural gas storage, because it is assumed that hydrogen is mainly needed in the industry sector we saw before, which shows rather minimal seasonal variation in the demand pattern. From 2045 onwards, the hydrogen demand is also in other end-use sectors, like the heating or electricity sector and transport sector, which is much more prone to seasonal variation. So this is the reason why the ramp-up of the seasonal hydrogen storage here is in the later years until 2050. What is not incorporated here in our analyze is, for example, load flow restrictions within the countries. So we look only with the exchange between countries. And also another aspect, what was mentioned earlier, is strategic options, like, for example, EU strategic hydrogen reserve or something like this. This is not considered. This is just the techno-economic optimization results here. So even when you think this is compared to today's natural gas storage relatively low, it is even a high challenge to reach that amount of hydrogen storage within 2050. In the next slide, you can see the development of the pipeline infrastructure within Europe, and also the connection to the selected MENA countries. So up to 2050, the potential to repurpose the existing gas infrastructure in Europe for hydrogen transport is really high. And the ramp up of hydrogen pipeline starts earlier than the storage ones. In opposite to the repurposing potential of the storage you see in the last slide, the repurposing potential for natural gas pipelines is much higher here in this case. In this scenario, you can see in 2050, that nearly 70% of the needed hydrogen pipelines are repurposed. You can see this in the lighter green bar on the right side. Compared to today's natural gas pipeline network, there's a significant lower demand for hydrogen capacity in our study here. So on the next slide, you will see then the geographical distribution of these installed capacities by 2050. From 2050, the figures show the need for a lot of repurposed, here on the left side, in the lighter green lines, pipeline capacity between the European countries, and especially new pipelines, which is here on the right side in dark green, from the MENA region, connecting the MENA region to Europe, especially between Morocco and Spain, Algeria, Italy, and also from Egypt or Saudi Arabia to possibly Turkey. Note that this is just a macroeconomic high level and technical analysis, which focus on cost optimization. As everyone know, each pipeline project itself is highly individual and considers other aspects than just techno-economics. So I will hand over to my colleague Jan to show another relevant dimension in our analysis than the techno-economic ones.
Yes, thank you, Felix, because it's a good point that you're making here, especially since the war in Ukraine. We've seen that that's the strategic issue when it comes to Europe's energy security has, of course, increased, and that other considerations also very much strongly comes into play. So what we've done in our study, we have referred to an option that was mentioned in the literature that concerns the proposed EastMed natural gas pipeline that was planned, and to convert that into a clean hydrogen pipeline that could transport clean hydrogen from areas around Sharm el-Sheikh, but also, of course, in the NEOM economic region that's currently being planned. Of course, you would have to consider a whole range of other topics that are actually quite sensitive. Of course, the fact that Israel would have to be or is also, of course, in play in like such a project. And of course, you would also have issues with countries such as Turkey, which might feel excluded in any kind of such a pipeline planning. So, but just to underline, we don't only look at the techno-economical part, but we also look at the more sensitive political strategic parts. So on that note, I want to switch now to briefly to also highlight a couple of results from our study, which concerns the MENA countries. So first of all, what we've done is we've looked at the production costs in the selected MENA countries. We've also looked at other indicators such as the cost of capital and a whole range of other factors. But what we visualized here is the calculated production costs of hydrogen for the MENA countries in 2030, which is the bar in green, which is the cost per megawatt hour. And we also have calculated the production costs of hydrogen in the MENA countries for 2050, with the bar in red being the mean value and also having a lower and a higher limit. What you can see here quickly is that the production costs in particular in countries such as Morocco and in Egypt are really particular low. We've also looked, of course, at the export potential, the technical export or the technical export potential of these 6 selected countries. And we've taken, like I said earlier, also the cost of capital. We've also made a calculation on that, but we've also taken into consideration aspects such as primary energy demand, the actual hydrogen production potential, on which I will talk a little bit more later on. And based on those various indicators, we have come up with the hydrogen export potential, the technical export potential. And what jumps out here is the enormous technical potential of countries such as in Egypt and also in Libya, and also to a lesser extent Saudi Arabia. The following image is a continuation of the previous image because it sort of flashes out where we see basically where we see this export potential. So, like, this is a GIST-based map, and it's based on some of the indicators that was mentioned by Felix earlier on. So it looks at the levelized cost of both solar and wind, but it also takes into consideration other aspects such as, for example, nature conservation, other unsuitable areas, distance to ports, distance to city, infrastructure. And based on those whole range of indicators, we've come up with optimal areas for PTX production. So you see in yellow for solar, and you see in the light blue the PTX potential optimal for solar and wind. And when we zoom in, for example, here, so you see from Morocco to Saudi Arabia, but for example, if we zoom in on Saudi Arabia, it's interesting to see that that our calculations are very much in line with the currently planned NEOM green hydrogen company factor that's being built, which you see here on the left-hand side. But our analysis also shows out that there's a huge potential for, in our case, hydrogen production in Saudi Arabia's eastern region. That's the oil producing region of the country, hence there the symbol for Saudi Aramco. So these are very interesting analyses that of course need to be fleshed out more, but they really are presented here as the basis for further and more in-depth research. Our partners for this paper, Geostock, they have engaged in providing a secondary literature-based and a primary technical estimation of storage potential of hydrogen in salt caverns. It has to be pointed out that this is a very rudimentary first step analysis, and so the figures that you show here should be more seen as sort of an indication that there's more research needed, because we're only looking at salt caverns. We have not looked at, for example, depleted gas fields and other kind of storage options that are available in these MENA countries. We've also only considered the most optimal salt formations, but it's definitely a very good indication that there's more research that needs to be done on this issue, because we don't have so much data for example, the MENA countries as we do for in Europe, as was just shown by my colleague Felix. So on that note, I now want to turn over to my colleague Richard again to talk a little bit about the socio-economic indicators that we've also discussed in our paper.
All right, thank you. So as we know, the analysis so far was on aspects of hydrogen production or capital costs in the selected MENA countries, but full analysis also depends on socio-economic factors. The example that is given here is political stability that you can see on the upper part of the figure. And political stability alone comprises a range of indicators such as government effectiveness, the rule of law, and also control of corruption. Political stability is just one of many factors. I think we have around 40 factors considered in our analysis when discussing the socio-economic potential of MENA countries. So if we put all those 40 factors together, we get a picture that is on the next slide. Perfect, thank you. We can see a map with the results of all of these 40 factors. So this is a map with socio-economic potential for a power-to-X economy in 2050. Please note that it's a very high-level analysis, of course, and we will have to go more into detail in the future. So what we can see, or more as a reminder, is that our technical economic research showed that the MENA countries like Egypt or Libya can supply large quantities of hydrogen to Europe. But what we can see here is that their socio-economic potential is much lower and stands in considerable contrast to that of most countries in Europe.
Yeah, this is a very interesting first analysis of its kind. I would say, because it's in general assumed that there's that any kind of hydrogen economy is sort of that would benefit everybody in sort of equal terms, especially, well, if we take into, like our case, the Europe-MENA region, the MENA countries, they can develop a lot of hydrogen production and export that to Europe, and that would be highly beneficial to both Europe and the MENA countries. But we see in our first high-level analysis that's not the case. Although, again, as Richard said, that needs, of course, further research. So on that note, I would like to finish our presentation. So first of all, on the left-hand side, we've tried to summarize basically the core points of our paper. First of all, what you see in the upper bar area chart is the fact that Europe will be highly dependent on imports over the coming decades, and that the selected MENA countries, and you see that in the lower stack bar chart, that the MENA countries could play a very important role in supplying, on the one hand, hydrogen by pipeline, and on the other hand, there's a role for ammonia via shipping. So again, I started by saying that this is not the alpha and omega, and that this analysis is also presented here as a starting point, hopefully, for further research on technical and socio-economic aspects of the nascent Europe-MENA hydrogen economy. And it should also be a starting point for testing the feasibility of strategies like Repower EU, because what our analysis has shown here is that that it's highly questionable that the targets that have been set by Repower EU that they can actually be realized. But that's of course something we will also discuss a little bit later on in the panel discussion. And of course, that any strategic focus on scaling up hydrogen production in the MENA countries for export purposes, they also need to consider socio-economic aspects and strict sustainability criteria. That's also something that we've clearly pointed out. So it's not as simple as getting some capital, getting an offtake agreement, and planting a bunch of wind turbines and solar panels and start producing hydrogen. No, there's a whole range of aspects that need to be taken into consideration when we start thinking about importing, when we as Europeans start thinking about importing hydrogen or ammonia from, in this case, countries in the MENA region. So on that note, I would like to finish our presentation and give the floor back to Marieke.